Here, I'm going to give an introduction to our work, a unified framework for layout pattern analysis with deep cultural estimation. By analyzing multiple layout diagnosis reports, we hope we can identify the underlying systematic defect distribution as soon as possible to improve the yield. Compared to physical failure analysis, layout pattern analysis reduces the cycle time from months to days, which is an efficient method to identify the root cause. Physical callouts such as logic location, defect classification, and physical location provide valuable information for yield analysis. Diagnosis reports narrow down the suspect area and accelerate the failure analysis to a certain extent. However, the resolution of diagnosis is still not good enough to identify the root cause precisely. Hundreds of suspect patterns are presented in one report. It is difficult to use the raw diagnosis report to produce an accurate defect distribution or select the best die for failure analysis. From this figure, we can see that there are multiple suspects reported in one netlist crossing layers, and there might only be one suspect that lead to the failure. From a machine learning perspective, this can be regarded as a supervised learning task with a mass of noise. To summarize the problem we want to solve, here we define the problem formulae. The objective of layout pattern analysis is to identify the true root causes of the systematic defect by analyzing a dataset consisting of diagnosis reports and layout snippets of potential root causes in these reports. Each report consists of several independent symptoms such as defects. Possible causes are also given along with several important properties. In this work, features such as the snippet, suspect snippet, DFM statistics, and defect categories are used. There are mainly two kinds of work that try to identify the root cause distribution as shown in the figure. The upper branch work uses the BaseNet to identify the root cause. Layout features are not used, which largely restricts their applicability to real tasks. The lower branch of work uses the clustering method to cluster similar layout patterns. Simulations are required to pick a single layout snippet for each cluster. We provide a unified solution to the volume diagnosis-based root causes layout pattern identification task. Both the pattern clustering and the root cause identification are taken into consideration. The critical root causes can be identified and high-resolution cluster snippets are provided for further analysis. The detail of contrastive learning and structural culture model will be introduced to explain how we model in this problem. The main idea of contrastive learning is to maximize the similarity between latent features of a pattern and its augmented version, and simultaneously minimize the similarity between latent features of inputs corresponding to different original patterns. According to this idea, we propose the deep layout snippet clustering model. Layout snippets is transferred to the Unicode latent codes based on an encoder network. The conventional k-mean algorithm is applied to latent codes for clustering. Now we got a distance matrix for clusters and equivalent snippets are clustered in the same group. Then we transfer the distance matrix to the membership matrix to present the relation between the snippets on clusters. With the encoder network presented on the previous page and the feature engineering here, we map the layout snippet from the layout space to clustering space, which compress the features. We use the structural cultural model to model the cultural relationship between the candidate layout patterns and root causes. We model the structural cultural model between the candidate layout patterns and systematic defects with a multi-layer perception. Average cultural effect estimation is proposed to identify true root causes from a large number of potential root causes using diagnosis reports and the results of layout pattern match. The average causal effect of each snippet on the target, whether it is the root cause or not, characterize the causal effect of the presence of each layout patterns on the systematic effect. The average causal effect is estimated through intervention on each element of the membership matrix. Ideally, the true root cause will present the most significant average causal effect on the systematic effect. One drawback of the intervention experiments to evaluate the average causal effect is we need to calculate the expectation of all data extracted from the diagnosis reports. It is time-consuming for inference. To solve this problem, neural network attribution is applied to multi-layer perception to speed up the inference. We conduct the experiment on several industrial layout designs in different scenarios to evaluate the performance of our framework. And the defect injection experiments adopt to generate the diagnosis data. From the tables, we can see that the proposed framework can get better performance than the baseline and a commercial tool. Even with a high noise ratio and multiple root causes, our framework still got robust performance. The diagram here presented a comparison between a commercial tool and our framework on the multiple root cause dataset. Our method outperforms the commercial tool in most cases with a large margin. We further evaluate the quality of the clustering results. The higher AI score indicates a better clustering results. Embeddings got higher scores than the row layout patterns, which means the proposed contrastive learning method is practical for clustering. With the advantage of deep learning and neural attribution, our framework got around 8.4 times speed up on average at inference. Thanks for your listening.